Hello everyone, my name is Abdul Mirdad and I'm a postdoctoral fellow at the University of Alberta. Today I'll be presenting my research on mass timber panel concrete composite floor behavior with inclined soft touching screws and insulation layer. First of all, we need to know about the mass timber panel concrete composite system in a short form of MTPC composite. A typical MTPC composite floor system, as can be seen in the figure, where the mass timber panel is connected with the reinforced concrete slab with mechanical connectors. There can be a potential gap in between timber and concrete in the presence of an insulation layer. Under out-of-plane bending loading, the mass timber panel at the bottom resists tensile stress, where the concrete slab at the top resists compressive stresses. An insulation layer is in place in between timber and concrete for allowing better acoustic, vibration, and thermal performance. The shear connectors, in this case inclined soft touching screws, which penetrates all three layers like concrete, insulation, and timber, allows for partial shear transfer and partial composite behavior. The structural efficiency of this composite system mostly depends on the performance of these interlayer shear connectors. The common fasteners used in composite system is soft touching screws, which is ductile. There is a substantial increase in the strength and stiffness of the soft touching screw connection if the screw is installed at an angle such as like 45° or 30° angle to the surface compared to the 90° angle. This system is promoted by designer in the construction of modern multi-story mass timber buildings due to its higher strength and stiffness to weight ratio, larger span to total depth ratios, higher incline rigidity, acoustic, thermal, and fire performance compared to the conventional timber-only system. Allowable floor span for the TCC system are often governed by the serviceability performance requirements such as deflection and vibration, which are directly dependent on effective bending stiffness. So the main objective of this study is to investigate the structural performance of MTPC composite floor behavior and the influence of mass timber panel, concrete thickness, insulation thickness, connector insertion angle, connector spacing, and the span. The material properties for the test specimen are shown in the table. So two types of mass timber panel, namely cross-laminated timber and blue laminated timber GLP, as you can see in the figure, was used in this study. The concrete compressive strength was 55.8 MPa and self-tapping screw was used as the shear connectors. So in the figure, you can see the self-tapping screws and the silent floor, which was used as an insulation layer. So this silent floor is specifically made for these types of composite system, which can absorb noise up to 26 decibels. 4-point bending tests on 12 panels with different configurations were performed to investigate the MTPC structural performance. So the MTPC test specimens with 12 different parameters are shown in the table. So the CLT and GLT was used as a mass timber panel, and their thickness were 105 for CLT, which is 3 pi, and 130 millimeter for GLT. Concrete thickness was used for 75 and 100 millimeter. Insulation thickness was used 0 millimeter, 5 and 15 millimeter. 0 means there is no insulation. There was two spans studied, which was 4.5 and 6 meters. And self-tapping screw of 11 millimeter diameter was used in cross pairs at an angle of 30 and 45 degrees. And there was spacing investigated 250 millimeter and 500 millimeter respectively. With these 12 different parameters, 12 specimens were fabricated. So the specimens were prepared by first placing the acoustic layer over mass timber panel and drilling the self-tapping screw into the mass timber panel with appropriate specification, as you can see on the top left corner. Then the formwork was installed to the side of the MTP to ensure that appropriate concrete thickness was achieved. Then the next step was to cast concrete on top of mass timber panel. The specimens were kept in normal shop temperature for 7 days after the concrete pouring. Then the specimens were stacked outside and wrapped with a turf for 28 days before bringing them into the lab for testing. A typical bending test setup of a specimen is shown in the figure. One end of the support was a roller over a pivot, while the other support was allowed to rotate but not sliding by placing wedge, as you can see in the last figure. The specimens was loaded through horizontal needle roll bearing face at third point along the span shown in the figure on the right. 4 LVDTs were used on the 4 corners, as you can see on the left side and the left picture for measuring the relative slip in between timber and concrete. In the midspan, cable transducers were placed to measure the midspan displacement. Here is one of the video of 4-point bending test. I'll go through the videos once it starts to play. So this is one of the 6-meter specimens with GLT. The top one is the load displacement, and the second one is the load slip performance, as you can see in the figure. The screw was at 30-degree angle in cross pairs. The maximum load was 91.7 kilonewton. So you'll see the concrete fracture at this location once it reaches its capacity. You can see here. Here you go. So after this failure, you saw that there's a steep drop. So in this slide, I'll show the load displacement response of this 12 specimen. The load displacement curve was obtained by taking the average midspan displacement from the cable transducer in the midspan and applied load on the specimen recorded by the calibrated load cell. Top green figure is for 6-meter specimen, and the bottom orange figure is for 4.5-meter specimen. If we see closely into the figure, we can see that 4.5-meter specimen in the orange figure there showed higher capacity compared to the 6-meter specimen. The 4.5-meter specimen had higher strength of around 75 kilonewton, where the maximum load for 6-meter specimen was found around 125 kilonewton. Also, you can see there is more displacement in 6-meter specimen compared to the 4.5-meter specimen. And I'll discuss this result more in detail in the coming slides. Here you can see the load slip responses of the 12 specimens. The load slip responses were obtained by taking the average slips near the end of the panel from LVDTs and vertical applied load on the specimen. Similarly, top green figure is for 6-meter specimen, and the bottom orange figure is for 4.5-meter specimen. As you can see, the red one is for the CLT specimen. So both in 6-meter and 4.5-meter specimen, there is less slip because the rolling shear happened in the CLT specimen and which failed earlier in the loading stage. Now I'll discuss about the load carrying capacity. Overall, you can see 4.5-meter long specimen showed higher capacity than 6-meter long specimens. The specimens with CLT showed lower capacity compared to the GLT specimen because of the higher thickness of GLT as well as weak transverse layers of the CLT. You can see number 5 and 6, specimen number 5 and 6 compared to 1, 2, 3, and 4 for 6-meter specimen. Similarly, number 11 and number 12 compared to number 7, 8, 9, and 10 specimen. The specimens with 30-degree angles showed higher capacity compared to 45-degree angle screws. This can be seen in figure 3 and 5, as well as specimen number 8 and 9. So when the screw was closed, so the capacity reduces in the presence of insulation layer, which can be seen in 1 and 4, where you can see there is insulation of 15 millimeter. That's why there is a drop of capacity. Similarly, it can be seen in specimen 8, 7, and 10. Once the screws were closely spaced at 250 millimeter spacing compared to the 5 millimeter spacing, the capacity increased significantly when compared, which can mitigate the reduction due to the presence of insulation. So if we see specimen number 3 and 5, so specimen 3 and 4. Specimen number 4 had 250 millimeter spacing, but it has 15 millimeter insulation. Although it has 15 millimeter insulation, because of the closely spaced screws, it has higher capacity. Similar result can be seen on specimen number 7 and 8. Now I'll go through the effective bending stiffness. The specimen with CLT showed lower stiffness compared to the GLT specimen in the 6-meter long specimen. You can see number 5 and 6 are lower than specimen number 1, 2, 3, and 4. There was a significant drop in stiffness due to the presence of insulation layer. Once we see specimen number 2 and 3, we can see because of the 5 mm insulation, the capacity dropped in specimen number 3. Similarly, we can see in number 7 and 10, where due to the presence of insulation, which is 15 mm compared to the 5 mm, it has dropped in bending stiffness. Then the specimen with 30-degree angle screws showed higher stiffness. Once we compare specimen number 5 and 6, we can see the 30-degree angle screw at higher capacity, although it has insulation layer of 15 mm compared to the 5 mm insulation in specimen number 5. In this case, closely spaced screw contributes to the bending stiffness significantly. Therefore, the reduction of the bending stiffness due to the presence of insulation layer can be mitigated by using closely spaced screws. Once we compare specimen number 3 and 4, we can see that specimen number 4, because of the 250 mm spacing, although it has 15 mm insulation compared to 5 mm in specimen 3, it has higher bending stiffness. The tested bending stiffness was compared with most widely used gamma method. When we compared the gamma method, we saw that it's predicting the bending stiffness of the composite system within 12% of the bending test results. Two major failure modes observed in the bending test. The first one you can see at the top is timber fracture, and the second one is rolling shear. No concrete crushing was occurred in the compression because of the higher strength concrete provided by the ready-mix concrete suppliers. Apply the timber fracture one. So all the GLT panels failed in timber fractures, where the CLT panels failed in rolling shear. Once you see the timber fracture at this point when the capacity reached. Here is a failure, and here is some of the zoom in pictures of the specimens within the timber fracture. The second one is the rolling shear of the CLT specimen. It's really tough to see from this point. So as the capacity reaches, the specimen will fail in shear in this zone. Failed here, but you can see once we zoom in here, you can see there is the rolling shear failure happens in the CLT. So the reason of observing rolling shear in the CLT specimen was due to the progressive yielding mechanism of the fastener. Under this progressive yielding process, there is an increase in the interfacial internal shear force in the connectors, which led to higher shear stresses in the transverse layer of CLT. Well, we can see that from the test, the capacity and bending stiffness of MTPC composite is influenced significantly by the mass timber panel type, composite span, insulation thickness, and screw angle. Closely spaced screws can be used to mitigate the reduction in capacity and bending stiffness due to the presence of insulation layer. And finally, the gamma method was found predicting the mass timber panel concrete composite effective bending stiffness within 12% of bending test values. I want to thank our sponsor Western Architect, Nordic Structures, and Rotoblast for providing the materials for this 4-point bending test. And I want to thank you all for attending to the presentation. Thank you.